distillation column modeling using Aspen Hysys. In this scenario, we are asked to distill a paraffin feed into light and heavy fractions from 1000 kg per hour of feed consisting of 5% ethane, 25% propane, 35% N-butane, 30% N-pentane, and 5% N-hexane. The feed enters at the fifth tray of the column with a reboiler and a full reflux condenser. The feed enters the column at 95 degrees Celsius and 1350 kilopascal. At the same time, the column shall produce 300 kg/mol per hour of overhead product. Condenser and reboiler pressures are 1300 and 1400 kilopascal respectively. Initial reflux ratio is 10. In all cases, we shall use Peng-Robinson fluid package. Now using Aspen Hysys, we are asked to determine the compositions of the overhead and bottom products if N equals 10 and N equals 20. The process flow for the distillation column shows the feed entering into the middle of the column and is fractionated into light fractions from the top and heavy fractions from the bottom. Now let's start simulating the process. First, let's define the components of the feed. The scenario indicates that we have C2, C3, NC4, NC5, and NC6 in our feed. Next, we define what fluid package we shall use. The scenario specifies the use of Peng-Robinson equation of state for this process. Now we define the flow and the thermodynamic characteristics of our feed. Let's rename our feed stream as feed. The feed temperature is at 95 degrees Celsius and a pressure of 1350 kilopascal. Feed flow rate is at 1000 kg/mol per hour. Then we define the compositions of our feed. The mole fraction of ethane is 0.05, propane is 0.25, N-butane is 0.35, N-pentane is 0.3, and N-hexane is 0.05. Now, it is important that the OK message should appear at the bottom of the screen. Now let's complete the information needed at the distillation column. First, we assign tags to all mass and energy streams going in and out of the column. Then indicate the type of reflux used. In our case, we shall use the full reflux. Then we specify the number of trays or stages our column shall have. Initially, we shall put 10. Then we specify what reboiler configuration we should use. Then specify the pressures of the reboiler and the condenser. Then we indicate the product flow rates and the reflux ratio. In this case, the vapor flow rate is 300 kg/mol per hour and the reflux ratio is 10. Finally, we can now run our simulation. Now, pay attention. We should be able to see that parameters converged. Otherwise, we're missing out something that Hysys cannot do its calculation. Now, browsing through the worksheet tab, we can now determine the characteristics of our feed, overhead, and bottom products. Another important details we can get from Hysys is the profile of our column. We can see the pressure, temperature, and flow rates at each stage of the column. Under Worksheet Composition tabs, we can finally see the compositions of our feed, overhead, and bottom products. You will notice that overhead products is enriched with light components, such as ethane, propane, and minimal amounts of butane, while the opposite is true for the bottom products, where heavy components are concentrated. So what's gonna happen if we increase the number of trays from 10 to 20? We change the number of trays from 10 to 20 and run the simulation as usual. Now we notice that the components are further separated when we use more trays. It is evident that using more trays inside the column, the overhead is further enriched with light components, while the bottom are enriched with heavy components. But we have implications here. Columns with more trays are tall columns. They are more expensive, hard to operate, harder to maintain than shorter ones. So you have to strike the right balance here between product specifications and operational cost.